Protective Hard Coatings, PHCs, tailored for classroom delivery. Slide 1. Introduction to Protective Hard Coatings. Welcome, everyone. Today's talk is centered on an exciting and high-impact area of surface engineering: protective hard coatings, or PHCs. These thin yet extremely functional layers have revolutionized how we enhance material surfaces, especially under harsh environments. I'm Dr. Arnab S. Bhattacharya from the Department of Metallurgical and Materials Engineering, and I'm glad to have you on board for this journey into surface durability engineering. Slide 2, Learning Objectives. Let's outline what we aim to achieve. By the end of this lecture, you'll be able to understand what PHCs are and why they matter, appreciate how they've evolved over time, identify key materials and structures involved, explore their real-world applications, and learn how they are processed and characterized. Slide 3. What are protective hard coatings? PHCs are thin films, usually under 10 micrometers, deposited on material surfaces to improve properties like wear resistance, oxidation protection, and surface hardness. Despite their small thickness, their impact is massive, especially in aerospace, biomedical, and tool industries. Slide 4, cross-sectional SEM image of a coated substrate. Here you see an SEM image showing a typical coated structure. Note the sharp interface between the coating and substrate. A strong interface with no voids or delamination indicates excellent adhesion. Coating materials like TIN or Al2O3 are dense and smooth, while the underlying metal, like steel, has a rougher, grainy structure. This contrast is vital for function and bonding. Slide 5, Applications of PHCs. PHCs find diverse applications. In aerospace, they protect turbine blades from high temperatures. In automotive, they reduce engine wear. MEMS, NEMS, and electronics use them for reliability. In biomedical fields, coatings on implants prevent wear and rejection. And of course, cutting tools benefit from reduced wear and extended life. Slide 6. The timeline of PHC development reflects technological maturity. From simple monolayer coatings, we've moved to more complex multi-layer and nanocomposite structures that offer a synergy of toughness, thermal stability, and resistance. Slide 7. Common PHC materials. We see a wide range of elements. Titanium forms TIN and TIC, widely used in machining tools. Boron gives rise to extremely hard coatings like TiB2. Silicon-based coatings like Si3 and 4 resist high temperatures. Carbon, in the form of DLC, offers low friction and high hardness. Nitrogen-containing compounds like TIN and CNC give chemical stability. Slide 8. Evolution of PHCs. We can divide the evolution into 3 main stages. 1. Monolithic coatings, simple carbides and nitrides. 2. Multilayers. These improve toughness and barrier properties. 3. Nanocomposites, the cutting edge today, offering nanoscale engineering and multifunctionality. Slide 9. Hardness chart of PHCs. This comparative hardness chart shows how PHCs surpass conventional materials. While bulk materials struggle under 10 to 15 GPa, advanced PHCs exceed 20-30 GPa, and some nanocomposites even go beyond 40 GPa, entering the superhard regime. Slide 10. Key properties of PHCs. We evaluate PHCs based on hardness and elastic modulus mechanical strength, fracture toughness, resistance to cracking, adhesion to the substrate, key for reliability, thermal stability, and oxidation resistance for high temperature performance. Slide 11. Nanoengineering in PHCs. Nanoengineering has taken PHCs to the next level. Smaller grain sizes activate the Hall-Petch effect, increasing hardness. Composite structures with nanocrystalline phases or amorphous matrices enhance crack deflection and barrier behavior, critical for high-stress environments. Slide 12. Fabrication methods. Key deposition techniques include PVD, high vacuum processes like sputtering and evaporation. CVD, chemical reactions at the surface deposit the coating. Sol gel and plasma spraying for large area or thermal barrier coatings. Emerging methods like hippiums and magnetron sputtering offer superior film quality and control. Slide 13, tribological and mechanical testing. Testing is essential. Nanoindentation gives local hardness and modulus. Scratch tests assess adhesion by controlled delamination. Ball-on-disc setups measure wear under realistic sliding. High-temperature rigs test oxidation and structural endurance. Slide 14, limitations of traditional coatings. Despite their strengths, traditional coatings can suffer from brittleness, delamination at elevated temperatures, poor adhesion on rough surfaces, and limited oxidation resistance. These are being actively addressed in next-gen coatings. Slide 15, modern PHC designs. To tackle earlier drawbacks, modern PHC designs involve superlattices, layered structures like tie-in, tie-ALN improving toughness and oxidation resistance, nanocomposites combining hardness and ductility, e.g. Tysin, multifunctional coatings, for example, biocompatible plus corrosion-resistant hard coatings for implants. Slide 16, case studies. 2 real-world examples. 1, Allison coatings on cutting tools push hardness above 35 GPa and increase tool life by up to 5 times. 2, DLC coatings on hip implants reduce wear particles, improving biocompatibility and patient outcomes. Slide 17, characterization techniques. Characterizing coatings requires multiple tools. XRD for crystallinity and phase identification, SEM-TEM for microstructural details, nanoindentation for mechanical response, AES-XPS for surface composition and chemical states. Slide 18, summary. To wrap up, PHCs are essential for advanced engineering systems. They've evolved from basic carbides to smart nanocomposites. Material choice and design must be tailored to application needs. Future research is focusing on multifunctional, self-healing, or adaptive coatings. The key literature guiding this field includes works by Viprek, Musil, and Zhang. These authors have made foundational contributions to the understanding and advancement of hard and superhard coatings.